The new problem from Pathfinder, challenge your understanding. And here we are going to see this problem. Once all of you please read this problem carefully. So let us read this problem once. Two identical beads A and B, each of mass m, connected by a light rod of length r root 2, can slide without friction on a fixed ring of radius r. The beads are also connected to two fixed points C and D with identical elastic cords, each of force constant K and relaxed length R root 2, as shown in the figure. Initially, the cords coincides with the diameter of the ring and the system is in equilibrium. Now the bead rod assembly is displaced slightly aside and released. So what will happen? Now the bead rod system will move. Okay. Find the acceleration of the point of intersection P of the cords immediately before a cord becomes relaxed. So this is the given question. So if you read this question carefully, so you will get some important points. So what are the important points that we are getting here? So here we can see the diagram. Based on the diagram we will get the clarity. A and B are two beads, and here a rod is there. This rod length is r root 2. This is a fixed length. Okay, and AC is a chord, BD is also a chord, and initially these chords are coinciding with the diameter of the ring of radius r. That means AC is equal to 2r and BD is also 2r. And here you can clearly see this is the point of intersection of the two chords P. Now let us see what will happen when we slightly displace the system. So that means here two beads are there, they are in equilibrium in this situation. If we slightly displace the rod, then what will happen? Immediately the beads A and B will start sliding on the ring of radius r. So now the point of intersection P will also change its position. Now here the task is to find out the locus of the point of intersection P here. Okay, so we are first going to find out the locus of the point of intersection of the two chords. What is the locus of the point of intersection P of the two chords? So that we are required to find. So if you see initially the angle between the chords, this is 90 and this is 90, because this is r root 2 and this is also r root 2. The points D and C are the fixed points, they does not change. So the distance between D and C is also fixed, that is r root 2. Okay, now I am going to find out the locus of the point of intersection P. Locus of point P. So here there is a intersection of the two chords. So that intersection is P. And when the beads are sliding on the ring, the point of intersection of the two chords will change its position and it will move on a path. So we are going to find out the locus of the point of intersection P. So now let us see here. For that purpose I am going to plot a diagram here. This is the diagram. So now you can see I have disturbed the system. Once I have disturbed the system, automatically the beads will start sliding on the ring of radius r, and definitely they will slide like this. This is in any intermediate situation. Okay, so at any time t. This is the diagram at any time t. Okay, so here this point of intersection P is here. Previously the point of intersection P will be here, it is coincided with the center of the circle of radius r, but now it is changed its position, and we are required to find out the locus of the point of intersection P here. So for that we are going to see some basics. So if you see the circle basics, so angle in semicircle, this angle is always 90 degrees. So this is very important point. You can take any any angle here, any angle. Suppose if I take this angle, again this is going to be 90 degrees here. Again this is going to be 90 degrees angle. So any angle in the semicircle is always 90 degrees. Okay, so you have to remember this point. And next point is, if you take this angle as 2 alpha, this angle is always alpha. Okay, so if you take this chord, so the angle subtended by the chord at the center is 2 alpha, then the angle subtended by the chord on the circumference is alpha. Okay, so this is also very basic points that we have to observe, and these are the geometry points, and these are very important in our discussion. So now let us start our discussion. So just see here, this angle is 90 degrees. Why this angle is 90 degrees? Because this is r root 2 and this is the radius r, this is the radius r. So this is a right angle triangle, so hence it is 90 degrees here. So you tell me, what is this angle? This is definitely 45 degrees. This angle is definitely 45 degrees at all times. This angle is 45 degrees because angle subtended by DC at the center is 90 degrees. So always this angle is 45 degrees. So angle DAC is always 45 degrees. And the similar manner, you can see the length of the rod is also r root 2. And angle subtended by the rod at the center is again going to be 90 degrees. Now if you see this angle, so this angle is going to be 45 degrees, always 45 degrees. During the motion, you can see it is always 45 degrees. Okay, so if this is 45 degrees and this is 45 degrees, you can clearly observe a triangle ADP, this triangle. So if this is 45 degrees, angle DAP is 45 degrees, angle ADP is also 45 degrees. So definitely angle APD is always 90 degrees. Always 90 degrees, because sum of all angles in a triangle must be 180. Sum of all angles in a triangle must be 180. So always this DPA is 90. So here you can clearly see APC are collinear. So this angle is also 90 degrees, because if you consider this APC collinearity, the total angle is 180 degrees. So this must be 90 degrees. So you can see DPC is always 90 degrees. If DPC is always 90 degrees, so the locus of point P is a circle with center as midpoint of DC. Center as the midpoint of DC, we are having a circle. Okay, so the locus of the point P is a circle. So that is the final conclusion. So we have proved that the locus of the point P is a circle. So now see the diagram. So this is the situation. So you can clearly see this is the point P. You can draw a circle with center on the DC. So this is the center. So here two centers are there. So this is the center O. So that is the center of the big circle of radius R, and this is the center O dash. That is the center of the circle of radius, which is equal to the half of the DC. I already know the DC length. So DC length is r root 2. So the radius of the circle O dash C is equal to r root 2 divided by 2, that is r by root 2. Okay, so the radius of the circle is this radius is r by root 2. This radius is r by root 2. Clear or not? So you can see clearly this point. So the point P is moving on a circular path of radius r by root 2. So this is the most important point. So locus of point P is a circle with center as the midpoint of DC. Okay. So now let us enter into the next part of the segment of the problem. So we have found that whenever the rod AB is moving, when the beads are sliding on the ring, the point P traces a circular path. The point P will also move on a circular path of radius r by root 2. Okay, but here they are asking us to find out the acceleration of the point of intersection of the chords immediately before a chord becomes relaxed. So if you see the initial situation, this is the initial stage, initial configuration of the system. Initially we can clearly see there is some extension or elongation, okay, in the threads or the chords. Okay, but if you see this diagram, this is the intermediate situation, but what is the final situation? So they have asked us to find out the acceleration of the point of intersection of the chords immediately before a chord becomes relaxed. When the chord becomes relaxed, when the chord length becomes r by root 2, then the chord becomes relaxed. Now let us see the diagram of the final stage or the final configuration of the system. So you can clearly see the final configuration diagram. So this is the final configuration diagram. So you can see this is the final state of the system. So this is the point A and this is the point B, and here point P is also there. It is coincided with the point B, and here C is also there, and B, P, C both all are coincided here, and this is the point D. You can see we are having the chord DB coincided with DC. The chord DB coincided with the DC, and the chord AC coincided with the length of the rod AB. Length of the rod is r by root 2. So the length of the DC we have already known that is r by root 2. So you can clearly observe. So this is a right angle triangle. So if you take this hypotenuse, you will get the full clarity on the diagram. This is hypotenuse, AD as the hypotenuse, and AB and DB are the adjacent sides. So in this situation we are required to find out the acceleration of the point of intersection. So this is the point of intersection. Okay, so here we are required to find out the acceleration of the point of intersection P. Okay, so now at this instant I am stating the velocity of the bead A as V, and the velocity of bead B is also V, because they are identical in all aspects. So the velocity is also identical. Okay, and here we are no need to worry about the any tangential accelerations, because here initially the system having potential energy. The total potential energy is converted into kinetic energy. Okay, and in this situation the speed is maximum, and hence tangential acceleration will be 0. So if you are talking about the acceleration of the point P, the point P is moving on a circle of radius r by root 2, and the acceleration possessed by the particle, acceleration possessed by the point of intersection P is only radial acceleration. Okay, so now I am writing the expression. So you can take the expression based on the axis. This is positive axis, negative axis, positive y axis, negative y-axis. And so this is the velocity of the particle, velocity of the point of intersection P. So this is the velocity of the point of intersection P, and this is the velocity of the bead. This is the velocity of the bead B. If you see, this angle is 45 degrees. So you can clearly see velocity of the point of intersection can be written as V cos 45 degrees. So you can write like this: Vp is equal to V by root 2. So this is very important point. And here we are applying conservation of energy. If you see initial configuration of the system, initial length of chord is equal to 2r. This is the initial length. Initial length is 2r. But the system is going to initial to final state. This is the final state. So here the length of the chord becomes r by root 2. So what is the final length of the chord here? R into root 2. This is the final length of the chord. So now we are going to write the expression for change in potential energy of the system. So you can simply write like half k into elongation whole square. Here two chords are there, so you are multiplying with 2. So half k into, what is the elongation? So you can simply write the elongation expression, and we are know the initial length of the chord as 2r, and the final length of the chord is r root 2. So you can simply write like 2r minus r root 2 whole square into 2. So this is the change in potential energy. So 2 can be cancelled, and you can take the r common. So kr square into 2 minus square root 2 whole square is the change in potential energy of this system. And in the final state, the chords are relaxed. So the total potential energy of the system is completely converted into kinetic energy of the system. Okay. So I am using the kinetic energy expression. So kinetic energy of the system can be written as half mv square plus half mv square, because two beads are there and they are having equal speeds, and we can simply write half mv square. This is the kinetic energy of the system. So we can equate the potential energy change and kinetic energy change. So from 1 and 2, what we can say? So we can equate 1 and 2, because the total P of the system is converted into kinetic energy. So that's why I'm equating. So what I'm getting, k into r square into 2 minus root 2 whole square is equal to m into v square. But here we are required to find out the Vp value. So I'm substituting the Vp value here. So that is root 2 into Vp whole square. So k into r square 2 minus root 2 whole square. So if we observe, we are getting the Vp square value as k into r square into 2 minus root 2 whole square divided by 2 into m. So this is the value of Vp square. But they are asking the acceleration of the point of intersection of the chords. I already told you. So here the acceleration expression is given by acceleration of the point of intersection is Vp square divided by radius. So the radius, I already told you, point P is moving on a circle of radius r by root 2. So I am just writing that radius here, and the Vp square value already we know that we can write k into r square into 2 minus root 2 whole square divided by 2m into root 2 by r. So this root 2 getting cancellation here, r are getting cancellation one time. Finally the acceleration of the point of intersection of the chords is given by k into r into 2 minus root 2 whole square divided by root 2 into m. So this is the final answer, and the direction of the acceleration of the point of intersection is in negative x direction. So we can clearly see here the direction of the acceleration is towards the center only, towards the center, because that is the radial acceleration. There is no question of tangential acceleration, because here the speed of the particles is maximum. So that's why there is no tangential acceleration. The only acceleration is the radial acceleration, that is towards the center. So I can write in vector form, acceleration of the point of intersection is magnitude of the vector and unit vector in the direction minus I cap. So I can write like this: the acceleration of the point P is minus I cap into kr into 2 minus root 2 whole square divided by square root 2 into m. So this is the final answer for the problem. Okay students, I hope you enjoyed this lecture.